Today I'll be demoing Mosviz, the second of 3 tools we'll demo as part of the JDAT framework. Mosviz is our multi-object spectroscopy analysis tool, particularly targeted to analyze data from nearest and near-spec MOS and JWST. This demo goes through a simulated nearest wide-field slitless spectroscopy dataset and demonstrates the MOS-specific features of Mosviz to help visualize and analyze your data. In this demo, we will attempt to identify a spectral emission line and model fit and emission curve. The notebook you'll be running today is the Mosviz JWebbinar Solutions notebook, which you can find here. I'll go ahead and open this panel here. It's under JWebbinar Prep, JDAT Session, and right here, Mosviz JWebbinar Demo Solutions. First, I'll go ahead and import Mosviz from the JDAT framework. So that's as simple as from JDAT import Mosviz, just like that. From here, we'll go ahead and create an instance of Mosviz by calling its constructor, very similar to Specviz. So just simple Mosviz equals Mosviz, just like that. Once we have that, the only thing we need to do to actually start up the app is to call it. So that's as simple as mosviz.app. I'll go ahead and execute this cell by hitting Shift-Enter, and you will note that the cell is executing by this little asterisk here on the side. And after some time, you should see the Mosviz window show up. Right now, it is a blank window because we haven't loaded any data yet, but that's entirely expected. All right. Before we can load our data, we of course need to download our data set. For convenience, I've included a cell right here to automatically download the data for you. So I'll go ahead and start the cell now by executing it. And again, I'll hit Shift-Enter to execute it. And this little asterisk here will denote that we're beginning our download. One note I'll go ahead and mention about this data set. If you observe with nearest wide-field slitless spectroscopy, you'll find that the dataset contains dispersed spectra along each axis, both the rows and the columns. For brevity, this dataset has removed the row dispersions to help facilitate load times and network congestion. Mosviz is aware of the specifics of nearest wide-field spectroscopy, so we'll expect Mosviz to warn us about missing row dispersions when we load it. This is entirely expected for this demo. While our data is loading, we'll take a preview of the layout of Mosviz. So I'll go ahead and scroll up here. Mosviz contains 4 viewers that facilitate the analysis of MOS datasets. Starting here on the left side, we have our image viewer. And then we have the 2D spectrum viewer sitting here in the top right. And the 1D spectrum viewer lives underneath of that. Across the bottom of the app, you'll see our table viewer that will populate with all of our dispersed targets we'll be loading in. Hopefully you see striking similarity between Specviz you had just seen and soon to be Cubeviz you'll see after this one that our colleagues have shown. As you'll see later, a lot of the features demonstrated in Mosviz are also available in Specviz and Cubeviz as well. As part of Mosviz, we've developed a data parser for nearest that understands the specific features of nearest wide-field slitless spectroscopy. The parser automatically detects the relationship between the files and relates them together in the table viewer. To invoke this parser and load the data we've downloaded, we simply need to call the single one-line function in Mosviz. That's as simple as mosviz.load nearest data. And then I'll go ahead and supply it with our folder above, which I've named appropriately, nearest folder. If you observe with MOS mode on JWST, you can replace this folder with your own data set you've downloaded. So go ahead and include your path of your extracted spectra. So I'll go ahead and start the loading process now. Again, Shift-Enter to execute that cell. This loading will take a moment. We're loading a lot of awesome science here. Again, as a reminder, this data set has stripped out the row dispersion, so we'll see a lot of warnings about missing R files. So you can see that little yellow pop-up right here. Again, that's entirely expected for this demo. So there are a couple of indications. Note this data has been loaded. There's this pop-up right here that says that the data has been successfully loaded. You'll see our table viewer has populated with all of our different data sets. As well as if we scroll down, you'll see the word done being printed after we've executed our data parser. So all those signals signify to us that our data has been successfully loaded. And at this point, you should see all our different targets in our table viewer. To switch between targets, you can click on the corresponding row. For this exercise, we'll be looking at source ID 6. So you can see right here on row indicated 5, we have source ID 6. We can go and press that. Now I will note, because another few users have specified this in the past, that this little checkbox here that isn't actually implemented right now, doesn't really do anything right now. That's for future functionality that we're developing. So you can just click anywhere along this row here to actually select source ID 6. And when I do that, you can go ahead and see the field of view is populated on the left-hand side, as well as the spectra for that particular dispersed target on the right. So you can see our 2D spectra and 1D spectra. Now, right now, you can't really see much here, but that'll be the intent of this exercise, to try and find something useful. With our data load, we're going to try to visually identify this emission feature I've been talking about. So as Ricky mentioned in the Specviz demo, we have included a good number of tools in our toolbox icon here. So you can open that by clicking that here. And you'll see an assortment of different pan zoom tools. So right now we're going to start in the 1D spectrum viewer. And we've included a bunch of different tools, including a bidirectional as well as individual axis pan and zoom tools. So using these tools, we'll zoom into our spectral feature that's located around 1.4 microns in this 1D spectral viewer. I'm going to be going through how to visually zoom, but if you're having issues zooming, I've included a cell in the solutions notebook to programmatically zoom into the region of interest after you've selected source ID 6. So over in the solutions notebook, here's that cell. So if at any point you run into issues zooming, you can just execute this one cell right here and they'll automatically take you to our spectrum that we're looking at today. But I'll be going over how to visually zoom. So first, I'll select the vertical zoom tool. So that's this one right here. And as you can see, as I click and drag around, that locks me into just zooming in the vertical axis. And then using my scroll wheel on my mouse, I will go ahead and try and zoom in to see if I can see a feature start to appear around 1.4 microns. And as I zoom in, I can start to indeed see some features starting to poke out here. As the feature starts to appear, I'll note the axis label on the left side to determine how bright this feature is. This will be important for our next step. So I'll just go ahead and note that the peak of this feature is roughly around 2 megajanskis in flux density. So I'll go ahead and keep that in mind. That'll be important for our next step. So what we're going to do is we're going to try to adjust our stretch so that we can see the spectral feature. To do this, we'll open up our toolbox icon here, and then open up our plot options by pressing on the gear icon. From here, we can go ahead and adjust how the data looks by clicking on the layer icon, or layer tab right here. And you should see a good number of common options you're hopefully familiar with in other image visualization tools, like opacity, contrast, bias, etc. We're particularly looking at stretch down here. And we're going to try to adjust our minimum and maximum stretch values to roughly be in that same region of the spectral feature. So I'm going to adjust our minimum to maybe be around 0, and then set our maximum to around 10, and that way our peak of around 2 megajanskis will be just in this field of view. And as I go ahead and exit from here, you can see this is starting to be a little bit more apparent. I'll switch back to the 1D spectrum viewer and try to use the horizontal zoom tool this time to try and zoom into a region of interest. So I'll go ahead and put my cursor around that 1.4 microns and go ahead and zoom in. The screen may flash a couple times. That's something we're working to improve on. But after it stabilizes a bit, you can see here one of our MOS-specific features that we built into Mosviz, that being our linked viewers. So as the field of view is adjusted in either the 1D or 2D spectral viewer, the other viewer will synchronously pan and zoom as well. The emission feature is becoming a lot more apparent in the 2D spectrum viewer and is aligned in both our 1D and 2D spectrum viewer, despite only zooming in one of the spectral viewers. This is because in this data set, our 2D and 1D spectrum share a relationship in spectral space. Again, if you're having issues getting to this point, please execute the zooming cell in the solutions notebook. I'll point that one more time right here. Go ahead and execute that cell if you're having issues zooming. But at this point, I'll go ahead and move into the next part of our demo, which is model fitting. So many of the features you've seen here and in other tools built in the JDAT framework are automatically included in Mosviz as well. We'll be demoing one of them here, that being the model fitting plugin that Ricky had talked about in his Specviz demo previously. This plugin is demonstrated to designed to attempt to fit a model onto the 1D spectrum view in the same way it would behave in Specviz. You can find our plugin tray on the right-hand side of JDAT under the plugin icon. And here you can see an array of different plugins we've developed, including the line list plugin that Ricky had demoed earlier. From here, we'll go ahead and select the model fitting dropdown to open the model fitting plugin. And just to give you a sense of what we'll be trying to do today, we'll be attempting a simple constant plus Gaussian model fit. To start, we'll need to select the spectral emission feature we want to actually fit. To do this, we'll do a very similar exercise that we did over in the Specviz demo. Open up the toolbar in the 1D spectrum viewer and select the region selection tool here. And then using your mouse, you can go ahead and select the spectral region here. And we have note that, as you see here, that there is a bug in Mosviz that sometimes when you interact with the feature, it will automatically zoom you back out to your default field of view. We apologize for the inconvenience here, so you may need to zoom back in to actually see the feature and see what you were able to accomplish. We're working to solve that before release. But I'm going to go ahead and adjust the thickness of the subset so we can see what we've selected here. You can see indeed we've selected this region here, the spectral emission feature that we're trying to fit. With the region selected, you can actually inspect your regions tray at the top of the app right here. And you can see that if you can see this inventory of all the different regions you've drawn. If this is the first region you selected, this should be named by default subset 1. So in the model fitting plugin, what we're going to do is for the data, we're going to go ahead and specify that we're going to be trying to fit against subset 1. So go ahead and select that. And then we're going to go ahead and add our models now. So like I said, we're going to be doing a constant plus Gaussian fit. So we'll need to add both a constant and a Gaussian model. So I'm going to go ahead and use this dropdown, select constant. I'm going to give it a name. This name should not include any white spaces, no spaces, and tabs, but you can provide whatever name you'd like. In this case, I'm just going to give it the name constant. And then I can go ahead and select add model. And what that will do is go ahead and add a constant model down here. And then I'll go ahead and repeat this for the Gaussian as well. And you can see I went ahead and added a constant as well as a Gaussian model. Next, we'll go ahead and move on to the model equation editor. And in this case, because we're doing a constant plus Gaussian addition fit, we're going to simply type in constant plus Gaussian, just like that. You should, of course, substitute in the names with the ones you provided above. You can adjust the name of the model if you'd like, but I'll go ahead and leave it by model by default and hit fit. And what that will do is execute our model fitting backend that we've implemented to try and do its best to fit. Let's see how well it did. And it looks like it might have zoomed out again, so I'll zoom back in to see how well that fit our emission curve. Now, if I zoom in, you can see it didn't do quite a great job. Just as a little secret, that was almost intentional, so that I can go ahead and demonstrate what you can do as a user to try and help the backend along if it doesn't do quite a satisfactory fit. So we can go down here to where we've defined our different models, and if you expand these boxes here, you can see the different parameters the system has gave an initial guess to the fit. So we're going to go ahead and scroll up here and take a look at our feature. So I can see here that our constant is just around maybe 1.4, let's say around 1.4 megajanskis. So I'm going to go ahead and adjust our amplitude or constant value to 1.4 here. I'll go ahead and inspect our Gaussian feature as well, because we had identified that this peak of the Gaussian is around 2 in flux density and our constant is around 1.4. Seems like an appropriate thing to say that the Gaussian is peaking around 0.6 above the constant. So I'll go ahead and adjust this to 0.6. The mean, like we said before, is around 1.4 microns. So I'll go ahead and also adjust the mean to around 1.4. And as far as that standard deviation, let's take a look at this feature here. Looking at the x-axis here, I'm going to go ahead and try to put in an intelligent guess of 0.005 microns. That seems to be about a fair guess for the standard deviation. Of course, these don't need to be anywhere too accurate because the system will try to iterate on what guesses you provided it. We'll go ahead and hit fit again to see if that we give the fitting backend a second chance here. I'll zoom in one more time. And let's see how well that second pass did. Looks like it did a much better job this time. Let me adjust the layer so you can see what we've been able to accomplish here. I'll make that blue. And actually, I might also adjust the line width as well. And you can see that did a much better job at the model fit. Now, of course, we could also be here and iterate a couple more times, but I think that's going to be all that I'll want to demo today.